Thank you to the committee to consider this talk at this conference, at this symposium. And I'm here in my role as the coordinator of this emphasis project, an European effort. And yeah, it's an honor for me to be able to give in the idea and also some first results of this effort. And so when I prepared this talk, I tried to take your position and build up a mental model of your expectation. And so this is the outcome. These are the questions, and I hope if I do a good job on this, that the only remaining question will then be, when can I have it? So, and then of course I also want to give acknowledgement to all the contributors to this talk. So, and then every model is not exactly right, and therefore I'm also happy to have a feedback round and have your real questions that I didn't answer at the end, of course. Okay, so coming to the very first question. I mean, why are you doing this? That's a very fundamental question. So the very fundamental answer to that is to save the world, one could say. Of course, that's a big goal. But I mean, even in these days, I think the new generation really put it into our faces that something has to change, that we cannot just proceed as we did and have to rethink certain things. And now the question is how to do that. What is a good approach? And given this community, I hope that I'm safe to say it should be a model-based approach, right? So this is what how I figured that. Modeling and simulation. I mean, you try to model the world. You build up your models of these tiny pictograms, finally being able to explain the world. And once you did that, then you can build better products. I mean, once you have a model, you can optimize it. And we have heard a lot in previous talks how that actually helps. But in fact, this is only one side of the medal. The other aspect is that modern products are really fueled by code. And the added value of software is growing. So this means really finding a way of bringing these two worlds together, physical modeling and embedded software development. That's really the big challenge. Building a bridge between these two domains. And this is really like the one sentence, if you wanted to put it into one sentence, the goal of this emphasis project. So let me put it maybe a little more pragmatic. I mean, the nice thing is that I've pointed out some examples of how models help to make better software. And we've seen that in previous talks. So we have seen virtual sensors, we've seen model-based diagnosis, and also like inverse controllers and MPC controllers. And that's really, I think, very interesting applications. But all these depend on that you have like this model and dissolve it into the software so that you can actually inject it into your controller. And here it's an example just to really illustrate the benefit and the value of doing that. Here you replace a sensor in hardware with a software. And I mean, especially in the automotive industry, whenever they can save 5 cents removing something, replacing hardware with software, they are overly excited. So that's a very valid use case of doing that. And I really see that these models integrated into control units are really a key enabler and a big effort for future developments. But you might say, well, okay, is that really new? I mean, we've been doing this for years and years. And I mean, we have our function developer, and he grew up with Simulink. and he's modeling the physics, and he's even deriving a controller from that, and then eventually he needs some numerical understanding to make sure that it actually runs also on the ECU. And yeah, and then there are all these coding guidelines and all these stuff. Okay, it's a lot of stuff. And to be true, that's, I think, one of the problems why this has not scaled as one would have expected at sometimes. Simply because there are not too many superhero function developers out there that really have this broad expertise to bring it all to the table. So what can we do about it? And one simple approach is to say, well, we have experts for physical modeling and we have experts for control engineering. We also have numerical libraries dedicated for specific things, and we have guys, a lot of software developers that are really knowledgeable about what is embedded software. So how would it be if we could find a workflow to separate these concerns and leave these guys use their preferred tools? Let the physical modeling expert have its hammer if he likes to hammer. Don't make him to do the cooking if it's just not his world. And this is the approach of eFMI to separating these concerns and leaving the people with their preferred tool to do their job, and then rather think about how to transfer the models between these different phases. So it's not by saying, I think a little bit what happened with model-based design by saying we model the software and made Simulink a kind of physical model, but at the end, I mean, it's coded, so it's drawing functions. And that's not really what we want, to pull the complexity of embedded software development to the highest level of abstraction of a physical model. You basically screw up the physical modeling if you do that. So it's much better to say it's a different level of abstraction, so we need to have a different way of modeling this. And let's delay the decisions to later stages. And let the proper experts make those decisions. And an implementation decision for an embedded device should be made by a guy that really knows what embedded software is all about. So at the end, we hope that we maybe not need it at all, but fewer superhero function developers and have very happy experts in their specific domain. So, but the other thing that you might say, well, we have FMI. So you say, well, this is new. And in fact, I mean, that's true. There have also been studies and papers and publications also from my colleague where this has been tried to run FMIs on embedded devices. So that works. And I think also in other areas, this actually works, as we have seen in previous talks. But automotive is special. I mean, you're very special demands on the memories, on the data types. And as of today, one must say there is no solution. It's simply not possible if you want to have a compliant and safe software, then you cannot use FMI as it is today. So what we intend or have in mind is a workflow like this, to having the eFMI more or less like a bus that can is a big container, and going through the different phases can really collect the content that is produced in the different stages and can even move back and forth. What would a toolchain look like? And here we see that there are several what we call model representations. So this equation code, algorithm code, production code, binary code are all different model representations, and there are transformations in between these representations. And there are different pathways. So, I mean, you might have a tooling that can go directly from a model to a production C code. But what we expect will be the most commonly used workflow is that you have a two-step approach. And this really reflects the idea of separating the concerns. So that you have this algorithm code really capturing the essence of the computation that has to be performed, and having the production code really capturing how it's implemented to distinguish the what from the how. And then we also want to support the equation code. And this is really, I think, what we've heard today about this model-based diagnosis. This is really supporting this kind of use case. That's also what we have in mind, especially at Bosch. But we will see that in a minute, what it means. The other question, of course, is, well, okay, this sounds all good, but maybe a little bit too magic. And this is the architecture that we finally came up with by saying, from the outside, it looks like a classic co-simulation FMU. The benefit of that is that even though there's an eFMI, an eFMU inside, any tool that supports FMI or will support FMI 3.0 will be able to import and run it and execute it at any simulation tool, which will support like software in the loop simulation cases. But a tool that is eFMI enabled will be able to identify that there's more in this box. And that's what this eFMU container is all about. So this eFMU container has what we call a manifest. And this manifest is more or less like the content description of what is inside there. And then there are these different kinds of model representations. And these are optional, so they don't have to be in there. Some are 0 or 1. And the production and the binary code can even be multiple. And why that is, I will explain in a minute. But you always have like this binary source code and model description, like from this classical FMU. And this is, in fact, a copy of one of the production codes or binary codes, so that you can have multiple instances of that in this container and can, so to say, decide which will be visible when you load it as an FMU. So now a little bit talking about these different model representations and what they look and what they are good for. So the equation code basically is flat Modelica. So a set of equations, a DAE system, and the purpose is really to capture the mathematical essence of the physical system. And here a code example is also given where you see like there's this derivative operator, you have equal sign, you can write an actual expression with the left-hand side and the right-hand side. And how it's specified is that we really want to collaborate at that point with the Modelica language working group, and will also participate in the Modelica design meeting tomorrow, and really team up to standardize flat Modelica. That's the goal, and I mean, this is just a first idea what keywords would be needed. The basic idea is just to get rid of this object-oriented stuff and not support algorithms in the first step, and really focus on these mathematical equations. Then we have the algorithm code already mentioned. I mean, this already looks pretty much like algorithms in Modelica language. And in fact, also this is a subset of Modelica, but has also some extensions. The purpose of this is really to be a logical representation, so an abstraction of the production code. And as I said earlier, it's really about describing what is this code supposed to do rather than how it's going to be implemented. And I mean, there's many more could say about this. I think most prominent extension is this methods keyword, I would say, so that there are predefined functions, but always is the idea to make this also extendable, so that you have you must have a do-step method. You can name it as you want to, but you can always define additional methods if you need them. So production code will be C code, and again, it's could be a generic code that can be compiled on different platforms. But the idea is to say, if you want to do embedded code, then it has to be as good as embedded code is today. Otherwise, the acceptance of that will go drastically down, because performance is really key. But to achieve a high performance, you have to take your target into account. So you have to become target specific, which in consequence means that the code for target A looks different than for target B. In the one case, you may use global variables. In the other case, you might have like a function where this is passed in and out. So that depends. So the conclusion was it doesn't make sense to standardize the API for the C code. In contrast, we must support that everybody can do its own thing. And therefore, this idea was to instead extend the model description by being a manifest in the sense that it describes of how this code has to be integrated. So if you get an FMU, you might find 3 different variants of production code in it, and then you have to decide which of these different implementations suits your needs. It can be that none of these really fits, and then you rather talk to the guy who created this eFMU to make sure that he's using a configuration that really meets your requirements. So, and then finally, there's also this binary code. I mean, the purpose is also to have IP protection, but then also to allow that this can be kept consistently in one package together with these files that you need for that target. And without going into the detail, I would move on to the question, how does it work in practice? So the good news is that we had a very good, very productive week, the last week, because we had a Plugfest, the first Plugfest of eFMI in this project in Runningen, and I think the developers really put in everything to have something up and running, and then there were also some iterations, and finally we get something to work. And here are first screenshots of the prototypes that are out there, and this is the workflow that we did. So the model, I mean, you won't be overly excited when I tell you it's a PID controller. Said I've implemented that before. Okay, I see. This is the tool chain to do it even better. We will see. But we wanted to start with something that we understand. And therefore, we are quite happy that we have, from all the various tools that are involved in this project, we had 2 vendors that actually came up with first prototypes with Daimler, where you open the model, so you see the system model with a closed loop circuit, and then you see the sample data system, and then you pick the instance of that controller, and from there you can start an export dialog and say, grab this instance and define a configuration with a sample period and a discretization method and dump it out as algorithm code. And very similar thing is possible in the Simulation X UI. You also have a export dialog and can do the same thing and get your algorithm code. So there's not only algorithm code this eFMU has this manifest, and here is just a view of what is written into this eFMU manifest file. So as I said earlier, it's like the content of this eFMU container. And really the idea is to have something that is unique, extendable, flexible, which means you can add more stuff to it. You can decide how you want to structure, if you want to have one file and two files, if you want to have subfolders and so on and so forth. So you have that flexibility, and that there is a mechanism for traceability. So you see this reference ID that really allows to reference across these different representations. And there's also this checksum. And that's also a quite important feature, because if you get this eFMU, then you can always see if something has changed and what has changed. Is the algorithm unchanged? Is it only the C code that has been updated? So that's also an important thing to really know where you are when you are handing around these eFMUs. And then we have this algorithm code manifest. And this is more or less the well-known model description of FMI with some extensions. But again, here it's about consistency, traceability, and extendability that has been improved. And then we come to the algorithm code. It's a readable, understandable form, really, of that computation that is performed. It's discretized, target independent, and that's really the key here. So this algorithm code can already be imported into TargetLink and Skoda Congra, two from ETAS. And here I only have a screenshot from the Skoda Congra tool. So you can import this algorithm code, and then you can generate production code from there. So here in this you even have it side to side. And also in the lower left, you see the manifest file that is generated for this production code. And all this is then written out as the production code representation. And this always, or should, it's optional, it should also come with an FMU. So that one can, if he wants to validate and verify this, for instance in TPT, can pick up this FMU and run it. And this is also something that already works. So TPT is able to read this eFMU container, generate tests, and verify the results, make sure that in a back-to-back testing, that going through all these transformations, it's still doing what you expect and what you want. And then there are also tools like Astre. They pick up the C code and can perform a static code analysis and really tell if all the rules are satisfied and make these rule checks and so on. So it's also a very important step when you talk about safety critical embedded software. And then finally, of course, you have some build environment, you have some framework for your embedded software, and you want to integrate this code into this software. And here it says manual integration, so this prototyping work is still ongoing. We of course also want to automate this this process. And the main idea in this early stage is really to run performance benchmarks. And this is like the build tool used at Bosch. And this also allows you to measure how much memory is allocated by this function, and then that you can really also measure the required CPU time. And the goal of all this is that we have, for each of these test cases that we have selected, and this is only one, and in the table you see what are the different criteria we have assigned to these test cases. So we really want to have a test case that deals with multi-dimensional maps, with large maps, and so on and so forth. And this is like a very simple test case. I mean, there's a limiter, therefore it's nonlinear, but rather straightforward. And always have a manual implementation of that same code, so that we can really say, well, okay, now we have this nice tooling, but the benchmark is the state of the art. And I mean, we would expect that we will not be as good probably, but still we are hoping that we can get very close to it. there are some measurements have been made. I mean, we're still working on this, so it's too early to put out any numbers here. But this will be very interesting in the future, I think. So who will use this stuff? And also just to mention, within the eMphasis project, we also have not only tool vendors, we also have OEMs and suppliers. And they really came up with a lot of different use cases. And this is a wide variety of different applications, of different control strategies that are covered by the demonstrators we will be working on. And also talking about the tools. So you see with this icon for the prototypes that we already have 7 tools supporting the current state of the work, and there are more tools to come. So I think this is a very encouraging to see that this standard is already embraced. I mean, there's still a lot of work to be done to really bring it to an end, but I think that's a very promising outlook. So yeah, and therefore I hope you have this question: when can I have it? Yeah, the eMphasis project has been extended by another 6 months, so February 21 is the final date until when we will want to have all prototypes finalized and the demonstrators implemented. And a first draft of the eFMI standard, I mean, we have internally released that, and we want to also consult the Modelica Association really to discuss what is a proper way to also align this with other activities and to really ensure that can be maintained in the long term. So these decisions have not been made, therefore it's too early to really say when this will be officially released. But we're also having a discussion how we can make this maybe under NDA available even before that official release, to also allow other tool vendors to pick up this new technology. Yeah, so this is the end of my talk. And at that point, I really want to thank all the contributors and partners of this project. As you see, it's quite a large number with 25 partners in 5 different countries. And especially, yeah, thank those that were present at the Plugfest and really accelerated things heavily over the last couple of weeks. So thank you for your attention, and I'm happy to answer remaining questions.